All right, so we were playing with the while loop before, and then I showed you the for loop, but the for loop's interesting. Oh, can you not see anything? Oh, I could barely see anything. Let's see if I can fix this. There. All right, that's much better, except for the fact that you can barely see anything. Every time you come into this room, they've changed the setup just enough to throw you off. Anyways, we were doing the while loops, and what was neat about the while loops is it'll keep looping while ever some condition is true. But then we also see the for loop here, and we used it with an example of strings. But there was also a for loop in assignment 1 that used it on a list of tuples, a list of coordinates. So if we go down here, and let's create a string equals hello world, and then we do for C in a string, print C. Great. Now remember, the variable name C is arbitrary. It can be whatever we want. It doesn't need to be C. The fact that I chose C is because they're characters, and it's just a good choice. In fact, maybe I should do like char. There. Now it might be a little clearer. But again, I don't have to say char. I can call it whatever. It's a good variable name. But here, like when we use the while loop, we usually, if we wanted the while loop to run a certain number of times, we would have that counter. We'd have to increment that counter, and we'd have to check that condition, initialize it, and all that. So let me go down here for a moment. Create a while loop. So while, 10, print, counter. And then counter plus equals 1. So there we go. We see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What value does counter have on line 5 where nothing happens? Yell out the answer. Who said 10? Raise your hand. Yeah, you're right. I tried to trick you. You got it. Why? Well, because counter became 10. And then we asked, is 10 less than 10? False. But counter is still 10. It's just that the loop didn't execute anymore. So if I print, we see that 10, because I printed it out at the end down here. So the counter, it's just a variable to keep track of something. Whenever you want to keep track of something, make a new variable or something. I noticed a lot of people yesterday in the labs, they were trying to get fancy, I think. Trying to use something in a spot because they think they should be using it there, but this is a classic case of you're thinking too hard. Slow down. I know I'm a broken record, but it's because you just slow down, take your time, and what does it say? The number of times in the lab I'd be like, okay, let's walk through your code. Like, oh, it's stuck. All right, well, walk me through your code. And people are like, well, okay, here, and then we get to the loop, and it's like, whoa, hold on. I literally want you to do every line of code. I'm not being silly. That's what programmers do, because as soon as you make a guess, as soon as you make an assumption, as soon as you generalize a chunk of code, you're in for trouble. So just take your time and think about what it is that you need to do. Don't think like, well, I know there's other variables. I definitely need to know, I need to be using that variable. Well, hold on, do you? Ask yourself that question and just take your time. So here's this. Now, if I create a string equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So here is a string, and I'm going to reset counter to equal 0. For something in ASD. Print counter. when I hit run on this chunk of code, in fact, I'm just going to take this down here, make a new cell. Take your time and look at the code. Little quiz for you. Take your time, look at this code, one line at a time, and get in your head what's actually going to happen when I hit run. I'll give you like 20 seconds. ASD is length 10. Okay, raise your hand if you've got an idea in your head. Raise your hand if you want like just 2 more seconds to get an idea. All right, I'll give you 2 more seconds. Okay, put your hand up really high if you have an idea. I want to see, really high and leave it up. So there's a lot of people without their hands up. Is it because you're not participating or is it because you're stuck? Because if you're stuck, that's fine. It's just use this maybe as a chance to kind of get a sense of what you do and don't know. So I'm going to hit run. Let's see what happens. Okay, put your hand up. Keep it up if you have an idea. Don't put it down. Up, high, 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 high. Okay, here's what I'm going to do. Keep it up. Don't put it down. I'm going to hit run. And you're going to keep your hand up if you were right. And be honest. Everyone was right. That had an idea. That's wonderful. Great. See, I tried to trick you a little bit. I tried to trick you because I was hoping, well, hoping's not the right word. And expecting isn't quite the right word either. But I thought maybe you'd be doing that. You're thinking too hard. You're trying to connect the dots. You see the variable something. But I never actually used the variable something there, did I? I could print it out, and every time it would print out the string 0, 0, 0, 0, 10 times. But the trick here is, what does the code say? No assumptions. And I think the lab, this week's lab, does a really good job at kind of kicking in the pants about don't make any assumptions. Part of the questions, for the half of you that were in Thursday's lab, you know what I'm talking about. For the half of you that are in today's lab or another lab, you'll see. But you'll have an advantage because I've given you the warning. So all that's happening is, okay, ASD is 10. Counter is 0 for something in ASD. How many times will this loop run if ASD is length 10? 10. 10, yes, good. 10. So counter, print it out, add 1. Print it out, add 1. Print it out, add 1 until you're done the loop. Yeah. Any questions about that? Because loops are still a relatively new concept. All right. So we saw how I can say like, okay, and then I could print, like, here, actually, let's do something else. Equals my string at location 5. Print a and we see I. Why? Well, 0, 1, 2, 3, 4, 5 is the I. So I can access an individual character from that string. We saw that. But I can even get that information, store it in a variable, and then print it out later. That's what I'm doing here. I know it seems a little silly. I'm just showing you what you can do. We had a big chat in lab yesterday about computer, programming. The computers, they'll do what you tell them to do. And I know that's often said as a joke, oh, if the computer doesn't work, it's because you made a mistake. Yeah, well, yeah, that's true. But there are all those rules that we follow. and the computer follows those rules. And you can do anything as long as you're following the set of rules that it allows you to do, which you're learning currently. But we can see some really interesting and funny things happen once we, I don't know, really start to follow the rules in unusual ways. But they're still following the rules exactly as they go. So, anyways, if I can access this character, I'm wondering if, okay, so if I can access it, I'm wondering if I could say like, well, my string at index 5 equals y. Okay? Do you see what I'm doing? Because I'm basically, when I do this, it's kind of like I'm accessing a value from a variable. I mean, effectively, that's what I'm doing. My string is a string, but I'm saying give me only a specific value at one of those indices. So I got that. Maybe I can do it the other way. Say like, well, instead of getting the value, can I change the value? It's a reasonable question to ask. So let's see what happens. No. String object does not support item assignment. We can't do this. This is because we call this immutable. It's unchangeable. Variables, all the other variables we've seen so far, even strings as a whole, well, no, not the strings, not the strings. But like the other things are mutable, we would say. We can change them, but the strings are different. The strings, once they're set, you can't change them. They're immutable. Why? Because. It's just the way it is. It's something to know. We will be looking at a lot of other things that are mutable, but that act like strings, like lists. But it's an interesting thing to observe. Now, all is not lost. If you really want to make a change, just one sec. If you really want to make a change, what you can do is make a new string that could be like, well, give me my string from the beginning to index 5. Oops. Plus, because we're going to string concatenate the character y, plus my string from index 6 all the way to the end, print my string. And we'll also print my new string. There. So my string is left alone. The variable my string is left alone. We got information from it, but we didn't make any changes to it. But I used the information from my string to create a new string that I stored in the variable my new string, and I printed it out. We can see that like, oh, it's changed. But it's not that it's changed. It's that we made a whole new string based on information from the other one. We never actually changed that string. Yeah, you had a question.
Oh, it was just at one point I wasn't sure if you said mutable or immutable.
So mutable is when it's changeable.
Yes.
Think of like a TV. You hit mute, you can do it.
Yes.
This is literally how I thought about it when I learned. Because I was like, this is weird. So you can hit mute on a TV. I can make a TV is mutable.
Yes.
But imagine you had a TV and you hit the mutable button, or you hit the mutable button and it doesn't work.
Yeah.
It's immutable.
Yes, and strings are that.
Strings are immutable. But we can still change them. We are not changing them, but we can kind of pretend that we are by making a copy. And then I can say something like, oh, now this might throw you off. And I want you to be honest. Watch carefully what I'm doing. And then you tell me if it sounds like what I'm saying is problematic based on my last rant about strings being immutable. My string equals my new string. Look at the code. Figure out what it's doing. I mean, you can look at the output. It makes it kind of obvious. But raise your hand if you're thinking, well wait, what? You just, huh? And be honest. Put your hand up if you don't like this. A couple people. I'll give you a second to still think about it. And then we'll see if we can figure out what the heck's actually going on. Nope. So, if I can do this right, okay, let me go back first to talking about this. The reason you might be thrown off, raise your hand if you're like, okay, yeah, wait, what? You just said you can't change strings, and I just changed the string, right? But in reality, I didn't. And here's why. This is where, raise your hand if you're thinking to yourself right now, okay, I'm no expert, but I'm starting to settle into this whole programming thing. Raise your hand, be honest, Yeah, people's hands are getting up. Okay, that's good, that's good. It might take a little longer still, that's normal. But I got bad news for you. This is where people, new programmers, start to go like, what? You are breaking all the rules that we just learned. But I promise you, we're not. But it takes a little bit of understanding to know why it works the way it does and how it's actually just following the rules exactly as it always has. So, when I have, go back to this. If I have, and we're going to go into this in a lot more detail in I think the next topic. But if I have an integer I, that's not what I wanted, I. Okay? And I say I equals 5. Right? And then I come along and say, oh, okay, well now I equals 6. Well, in RAM is kind of like set up like this, right? And each of these little cells holds information. That's like what I was talking about last time where people are sitting in different chairs. Okay? But I can put an integer in one of those chairs. So I can say, well, I means this thing here and it's got a 5 in it. And then if I come along and, wait, let me hit pause for a second and say, this is technically not how Python actually really works, but Python pretends to work this way because all the other programming languages will work this way. FYI. And remember that I'm not teaching you Python, I'm teaching you intro computer science. So don't panic about that. When I come along and say I equals 6, well, the computer's going to go, oh, okay, well, here, let's make this a 6. There, we're all good. Forgive my poor drawing with a finger, but that's what we have. Great. Now, you remember, though, that strings are kind of problematic because I can put an integer right there. And then I can put another integer in that chair there, or that chair there, or that chair there. But with strings, when I create a new string, how much room is it going to take up? Right? It might need, if the string's like hello world, okay, however many characters that is, but if the string is like, I don't know, the first chapter of Harry Potter or something, well, it's going to take up a lot more than just like 9 characters. So when I have a string, I don't really know how much room that string really needs in order to store it offhand. For an integer, I do. All integers fit nicely in those seats. They fit nicely in those boxes. Strings are different. So here's what's happening. I'm going to go back now. When I create a string, I'll call it S or something, and I say S is hello. Well, what really happens is I create in RAM somewhere, in one of those nice little boxes, I'm going to have S be a label for one of those nice boxes. But what's really happening is over here, somewhere else in RAM, where I had a lot of free space, the computer's going to go, oh, okay, so we got the string hello, H-E-L-L-O, right? And these are all in their own little boxes, because I can put a character in one of those boxes, so I know how much room a character takes up, but the string, I don't know, maybe the string is like hello times a million, and it just goes on hello, 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 hello. So what I'm not allowed to do is say, okay, my string, oh, let me take a step back. I missed something here. So s is this variable, but what s really is it's the information on where the string is. And remember, like I was talking about, it's offsets. If I say, go to the string, offset 0, it's h. Go to the string, offset 1, it's e. So what I am not allowed to change is this, the hello part. I cannot change that string. That string exists. It is stuck at that. When I say, give me s at index 2, it'll go, okay, s, okay, that's here in memory, wherever that is. The actual address doesn't matter so much to us. We index memory with memory addresses. If I didn't say that, that's what I meant. So go to s, and then give me the thing at index 2. Okay, 0, 1, 2. Okay, that's this. And I can't go to this and be like, oh, become a new letter. We can't do that. That's no good. Now, if we go back and look at the code, what I actually said here was my string, my new string. And this is where you may have been thinking, you just said you couldn't change what my string is. No, I said I can't change what the string is. The variable was called my string. Just give me a sec. The variable is called my string. And it gets me to a string. I cannot modify that string. That would be equivalent to me saying, I am not allowed to modify this. This is the actual string. But s, I'm allowed to modify. So if I come along somewhere else in RAM, maybe it's over here, and I create a new string that's, I don't know, who cares what it is? Blah, 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 blah. It's full of letters. When I say s, you equal this other string, it goes, oh, okay, well, here, you're not going to get me there anymore. You now get me there. So I can change what s is, but I can't change what the string is. If at this point, so you had a question? Never mind, okay. If at this point you're thinking, no, this is weird, you're normal. This is usually where people get very, very frustrated. Because just as soon as you started to get it, it feels like this is a bit of a curveball. We are going to be practicing this a lot. And it will soon become second nature, so don't panic, okay? The only way to get good at this, though, is practice, and that's why we're going to practice it a lot. And you've all been practicing, right? Sure you have, yeah. Maybe? Well, you should. Nope, don't save that. All right. No, that's what I meant. All right, so let's get back to the here. All right, so in. In is an interesting operator that actually is what we call context sensitive, meaning that it'll act differently based on how you're trying to use it. Same thing with like the plus symbol. If it's two integers, what does plus mean? Well, it means addition. If it's two strings, it's in a different context. It means concatenate the strings. In is going to work kind of like that. We will look at one of those uses of in right now. It's really handy. So if I wanted to check, for example, okay, if I wanted to check, okay, for L or char in my string, if, I don't know, the character L is equal to char, you know, I'm going to write that the other way. Char, no. There. Okay, I'm going to hit run on this. And all I'm doing is basically checking if the letter L is in there. And of course it's true. Well, it said true twice, I guess, because there's two of them. If I want to check if the letter P is in there, well, nothing happens because P is not in there. So we can easily check if a given character is in a string just loop through the string. Look at each character in the string and say, okay, is this character the one I'm looking for? Yes or no? Is this one the one I'm looking for? Yes or no? That's it. But we can, in Python, we can even do this a little easier. We can say, I'm going to get rid of all this. I can ask you, is L in my string? True. So in is a nice handy way of just saying like, all right, are you in there? Seems reasonable, right? Now the good news is, yeah, Python gives this to you. The bad news is most programming languages don't. So if you carry on, you'll have to get used to doing it the other way, which is fine. In fact, usually when I'm programming, even if it's in Python, I tend to not use the overly Python-y specific things that might make my life easier, but I avoid doing that because when I do it the way that's more consistent across multiple languages, it's perhaps a little easier to understand for everybody. So just FYI. I usually avoid making it too Pythonic. All right. So, okay. You are all, if you've got your computer here, you're going to take this function, put it into Colab, and tell me what's wrong with it. It's a function that takes a character and a string, and it basically wants to check if a given character that you provide to the function is in the string that you provide to the function. So, take this function and see if you can find out what's wrong with it. I'll give you a couple minutes, because this one's a good one. This right here is a classic example of early programmer mistakes by trying to do too much at once, not slowing down. So give yourself a couple minutes to do this one. And I know that a lot of people were working on assignment 1. Effectively, actually had an issue very, very, very similar to the issue that's wrong with this. I mean, based on what I put there, it looks correct, right? I mean, I tested the function twice, gave you the right answer. It's really quiet, so just raise your hand if you think you have an idea about what's wrong. 2 people. Okay, is it because like you're stumped, or you just need a little bit more time to think about it? More time? All right, I'll give you a couple more minutes. I don't hear much typing. The best way to find out what's wrong with this is to just play around with this function, see if you can break it or something. Okay, one of the best ways to learn anything in programming is to play with it, see what happens. So, the first question I'm going to ask is, raise your hand really high if you know what's wrong with it. Okay, not that many. Now what I want is, raise your hand if you don't know what's wrong with it, but you know it doesn't work. Because you tested it and something went off. Something was not right. I'm willing to bet you did something like this, because clearly all of these cases are correct. I checked if H is in that string. Well, H is in hello. Z is not in hello, and P is not in hello. True, false, false. Looks good. But if you're a lazy programmer and you don't do your testing very thoroughly, you're actually in for a big surprise later, because let's see what happens if I look for the letter L. This is great. This is obviously true. There's two of them in there. So let's see what happens. False. What the heck is going on? It's saying false. L is clearly in there. How is that possible? Well, the trick to figuring this one out is, guess, what does the code say? So let's look at the function. I put in an L and I put in an H. So char is L, string is hello. I said H, I meant hello. So, now work with me here. Count starts at 0. Is count less than the length of the string? Well, hello is 1, 2, 3, 4, 5. Well, yes, of course. 0 is less than 5. Then I ask, if string at index count, so what is the string at index count right now? Yell it out. H. All right, wake up. Earlier in the semester, I was commending you guys on how interactive you were. Don't turn into the group I had last year, I tell you. You're better than that, aren't you? All right, come on. What letter is that? H, of course it is. And then I ask the question, is H equal to char? Well, char is L. Is H equal to L? Who said no? Get out of here. Let's try that again. Is H equal to L? Of course it's false. So, we do not go into this condition. We go to this condition, else. And what does it say? Return false. But what's the catch with return statements? It stops the function immediately. The function stops running and it returns to the calling line. So basically it says, well, H is not equal to L, so return false. Return false, print out false. We never actually looked at any of the other letters. The way this code is written, we'll only ever look at the first letter. That's why we got lucky for checking if H is in there. Because if we are looking at the case when char is H, okay, is a string at 0, which is H, equal to H? Yeah, all right, return true. We got lucky. We got really lucky. Everything else would be wrong. Now, this right here is an example. Now listen up. This is an example of what I would call, what we would call a linear search. Let me ask you something. Worst case scenario, if this was implemented correctly, where you got to look at all the letters, and the string has length 5, how many letters would you have to look at to know that a given character is not in that string? 5. That's not a trick question.
I was going to say, not a trick question, right?
If there are 5 letters, and you want to know if any other given letter, like I'm asking Z, in the string hello. Hello has 5, length 5. How many letters should I be looking at in order to conclude that Z is not in the string hello? 5. All of them. I cannot conclude if a character is in a string until I've looked at all the characters in the string. It's like saying like the computer cannot conclude if a letter is in there if it hasn't looked at all the letters. Does that seem reasonable to you? Yeah. Any questions about the statement I just made? Ask, because it's very critical that this makes sense. This right here is probably the first example of us implementing our first real, non-trivial algorithm. Linear search. It's the classic, all right, here we go. This is a real algorithm now. Everything else you've done is an algorithm. But this is our first, like, real one, for lack of a better term. It's really, so calling it the real one isn't the right word, really, but, you know, it's our first non-trivial good one. So, the trick to this is to fix this. Let's talk about fixing this. How do I fix it? Well, if any given character, let me put it this way, listen up, because I want you to answer with me here. If the character I'm currently looking at in the string is equal to the character I want to find, what can I conclude? It's in the string. Remember, computer scientists, we're too stupid. I'm not going to use your questions. So if I'm looking at a character in the string, and I'm looking at a character I want to find, if they're the same, I can clearly conclude then, well, therefore that character is in the string. Right? Yeah. Okay, the quietness here is really concerning me, because I don't know if you don't understand, or what? It's Friday. I got bad news for you. There's a lot of Fridays.
I don't know when you want me to say true or yes.
This one wouldn't really matter, I guess. But so you were too nervous to answer? Let's try it again. You're all adults now. Friday doesn't give you a free pass. I have a character I'm looking at in the string, and it is equivalent to the character I want to find in that string. Can I conclude, like, what can I conclude? It's in the string. If the character I'm looking for is the character I'm currently looking at in that string, great. Think of it like this. Here we got a nice good group of people here. If I'm looking for someone wearing a black shirt, so that's you, but I start over here. I go, okay, are you wearing, no, let's start again. I'm looking for someone wearing a white sweater that says Xavier. And I look at you and go, oh, well, I'm looking for someone wearing a white sweater that says Xavier. Can I conclude that there is an individual in that row that is wearing a white sweater that says Xavier? Yeah. If at this point you're being like, come on, he's being like overly, like, is he trying to dumb it down for us? No, this is how stupid the computer scientists are. We can only ask and answer dumb questions one at a time. So, if this person is wearing a white sweater that has Xavier on it, written in black, I can conclude that there is a person in that row wearing a white sweater that says Xavier in black. Correct? Yes. But let's say I'm now looking for someone wearing a black shirt. And I go, okay, I'm looking at this person. What can I conclude about whether or not someone in that row right there is someone in that row wearing a black shirt? I'm looking at Xavier right here. I can't conclude a single thing. The only thing I can conclude is, well, it's not the first one. But I don't know, maybe it's further down the line. So let's go to the next one. That's not black, that's like a...
It's blue.
It's blue, perfect. Is that person wearing a black shirt? False. No, it would, either or is fine here. False. So what can I conclude? All I can conclude is that person is not wearing a black shirt. I cannot make a single conclusion yet about the rest of them. The point I'm making right now is, as soon as you find the thing you're looking for, you can conclude that that thing is there. If you are not looking at the thing you're looking for, you can't conclude whether or not it's there or not. There being in the collection. So if I go to the next one, now we have yellow stain effects. Are they wearing a black shirt?
No. False.
False, great. Black shirt, are they wearing a black shirt? True. Oh, now I can conclude. I can finally conclude. I cannot have this function stop running as soon as I find as soon as I find someone not the same. But the way this is written, it does, because it says, if they're the same, return true. If they're not the same, immediately stop and return false. That would say, are you wearing a black shirt? No, okay, then I guess it's not in there. Which is, of course, ridiculous. That's not correct. So there is a very simple solution to this. Solved. If we find it, there, now it's solved more precisely. If we find it, return true. If we don't, do nothing and carry on in the loop. If we ever get to that end, if we ever get to the row, let's say I'm looking for someone wearing a pink shirt. Are they wearing a pink shirt? Pink shirt, pink shirt, pink shirt, pink shirt, pink shirt. Now what can I do? I can conclude no one in that row is wearing a pink shirt. And I was only able to make that conclusion until I looked at all of them. So let's have a look now. Huzzah! It works. So this is a linear search. This is your first non-trivial beefy algorithm. And I guess it's not that bad, because I know a lot of you are like, come on, he's being like facetious about it. You know, he's dumbing it down for us. No, I'm not. I'm asking the simple questions that I'm only capable of asking. Anything more complicated I can't do. Don't impress me with how good at thinking abstractly in bigger picture you are. No. Show me you can be as dumb as me. That's what I need you to do. If I have a string of 5 things, how many things must I look at to conclude that this thing is not in it, assuming it's not in it? 5. What if it's 10 things? What if it's 100 things?
100.
What if it's n things?
N.
All n of them, yeah. What's interesting about this algorithm, and what I'm going to talk about right now, is we're starting off on, like, perhaps the simplest non-trivial algorithm. Computer scientists don't just code. We start to geek out about that algorithm. We start to say, okay, so let's say I make the input 10. The input in this case being the length of the string. I got to look at all 10 of them. Let's say the input is n. Okay, I've got to look at all n of them. But now let's say I double it, where the input is 2n. How much more work do I have to do based on if I double the input size, how much more computing needs to happen? Double. What if I quadruple the input size? How much more computing needs to take place? Quadruple, yeah. This right here, it's a linear search. You start at one end, you just go in like straight line to the end. But it's just 1 second. It's also linear in the sense that as the input size gets bigger and bigger, the amount of computing you have to do grows linearly, proportionally. If you double it, it doubles. Sometimes there are quadratic things, where if you double the input, it actually goes up by 4. The amount of computing that needs to happen. Yes?
Is this something similar that we used for the Starbucks question?
It is exceptionally similar. In fact, it is effectively... The Starbucks assignment was a linear search. Does this thing exist in there? Yes or no, count it. Does this thing exist in there? Yes or no, count it. It was a slightly modified one because we weren't just returning true or false. We were keeping a count, but you are absolutely correct. That was a linear search. So secretly, you've been doing it for a while now. Any questions about that linear search, though? I love linear search. I love it. Any questions, though? Yeah? That's a subjective answer. Trivial, I can't really answer that. That's a very subjective thing. Really what I meant is all the other algorithms we were coding ourselves before were like, okay, write a loop to count to 10. It's very specific. This thing right here is a very common algorithm that you see all the time in programming where it's like, okay, look through this thing. Now, you want to know something interesting? Searching. Raise your hand if you ever had to search through a collection of things before ever in your life. I'm not talking about programming. I mean, if you did assignment 1, you did it in programming. But of course you have. You've had to search through something. And chances are, if you're searching through it, you start at the top, and you're looking to see, oh, the thing I'm looking for is in this pile. You start at the top, and if there's n things in that pile, and let's say the thing you're looking for is not in that pile, how many things you got to look at? All of them, all n of them. You've been doing this. You have been doing linear searches your whole life, whether you like it or not. But I'm willing to bet you never really thought about it as formally as this. You never had to put it in code, because you never had to really break down the steps you were doing, because you were capable of just like, well, yeah, I'll just look for it. But this is what you were doing. This is the algorithm you were using, whether you realize it or not. Look at the first one. Is it what I'm looking for? No? Keep going. That's it. That is the algorithm you were employing. Now, you want to know something very interesting? It's possible to do a search where, so with a linear search, if I double the input size, how much more computing needs to take place? Twice as much. Later in the course, we're going to see an example of a search where I double the input size, but I only need to do one more thing. It's crazy. Anyways, we'll look at that. Oh, you have a question?
Yeah.
Sit!
With linear searches, is there a way to make it so that instead of just counting it to organize it into different lists?
I'm not sure what you mean.
Okay.
All right, now you can go. Just come up here.